Janeiro, Fluminense Federal University. He will talk about quantum thermodynamics, transport and strongly coupled systems.
Hello, good afternoon. So there was no mistake, it's strongly coupled, not strongly interacting. When Rodrigo asked me, invited me here to come, I had high hopes to conclude another project where I will just fit in beautifully in the workshop, but actually we don't have enough results to present, so I'll present the results of this paper here, which came this year out and actually deals with quantum thermodynamics in transport of electrons. So the main motivation, and it's a growing community of quantum thermodynamics, is actually to build very, very small engines. And people are hoping that you can actually combine things in a scale of microns and nano and do things that will produce work in a useful way. And all this has very tight relations with quantum information, and also one has to think about devices where all these beautiful things will work. And so being from the community of electronic transport, we were asking ourselves about what is actually the entropy production when you when you have current flowing into a nanoscopic ballistic device. And it turns out that this question seems very simple, but it has some subtle issues that one has to understand. And so before I go into the main part of the talk, I will convey you some of the impressions of the discussions which are being ongoing in this community about how you tackle this problem. So just not to, I like to begin just with an experiment, just to say that this is not just abstract thinking. And there is actually a growing community in doing quantum thermodynamics in electronic systems. There is even a review paper a number of years back. And basically, the setup is that you have a classical drive, right? And you do something to your system, and the system will actually respond. So we'll be doing a linear response. And will generate, the electrons will go out, generate some heat. And the idea is that there is some work that, depending on the setting, you can actually think about some work that these electrons are ready to deliver to an external system. So one of these demonstration experiments on how these ideas work is contained in the two sort of recent papers by the Pecola group. And they were analyzing behaviors of single electron boxes. So you basically, it's a classical setting where you have a superconducting box, which is interfaced by a normal metal, and it's driven or controlled by a SCT, a single electron transistor. And basically, you actually perturb your system, and you perturb the chemical potential or something like that, and you induce tunneling from this back and forth from this device. And these guys, they are very skillful and then can actually measure electrons as they flow back and forth into the single electron box. And this is very nicely done with time resolution. And depending on your drive, you have different responses. And actually, you know that once an electron goes from a region with a high chemical potential into a region with a lower, it will basically carry on energy, and this energy will be dissipated here. And this is associated to the heat. And in these very, very small systems, people were able to measure this heat or the work. It has some convolution with the work that has been done in this setting. And they were able to show that all this satisfy known relations in let's say, stochastic thermodynamics, like the Rajinski equality, et cetera, et cetera. So it is a demonstration that even in this nanoscale devices, the laws that have been derived for classical systems, if you wish, they are satisfied to some extent. And more than that, you go to situations where fluctuations are very important. So, and this is the next step, and I ask you for the indulgence. So let me begin with the outline. So I'll begin very simple, and I hope you don't get bored. I'll talk just about this issue of the classical limit in the nanoscale, and then I'll flash one of the big problems that we are dealing here, which is the strong coupling limit, and then I'll go to the real stuff of my talk. So, and here I'll go several steps back, and you can relax. So you setting the stage, like equilibrium quantum statistical mechanics, real old stuff. So this I actually extracted from my lecture notes. I hope you don't mind. It's pretty obvious this is in Portuguese, but it's a small system, large system. And if you work in the grand canonical ensemble, what you learn how to do in school is that if you write a classical Hamiltonian of your system and you decompose into this partition, you can associate normally a fraction of particles which basically live in this interface or nearby this interface, and assuming that the system is large, so the volume contained by the fraction of particles living here is much smaller than the volume here and here, and if the interaction is kind of reasonable interaction, not infinitely long-ranged, you can actually neglect all the interactions between particles in both systems. And then the whole machinery of StatMech, you can crank and obtain a canonical partition function. From that, you can obtain the grand canonical density of representative points, the grand canonical partition function, all that, just by the fact that you have two systems that are actually coupled, but all the particles that live in interface you don't have to worry about. So the Neyer number is much, much smaller than the rest. And then you actually, and this is the last thing, sorry. And then actually you have this recipe that you can compute all the statistical, equilibrium statistical mechanic properties or things just by the knowledge of the partition function, taking the traces of the partition function, writing the free energy like that, or writing the grand thermodynamical potential like that, and then you rederive the whole thermodynamics. So why is this interesting or important for us here? And the issue is that once you have a very small system, right? So suppose that whatever is in this box is a very small system, like a molecule or a quantum electron box, then by no means the number of particles in this subsystem is large as compared to the number of particles in this neighborhood. And so you're not entitled to throw away this coupling, and things can get really messy. Well, this has been noticed a long time ago, actually, by this gentleman who already wrote a book on that, a very, let's say, pioneering book when nobody was really thinking about small systems. And then he wrote, actually, many years later, a Nano Letters, where all these ideas were beautifully explained. And this is a problem that has, I mean, still in current, let's say, investigation, how you treat this coupling, even in classical systems. So, for instance, I just selected one where Chris Jarczynski was interested in knowing the work that a pipette will do, or the laser trap will do by stretching RNA molecule. And this system here is not that small, but the size of the handles that you have to couple to them is really gigantic, and you cannot really neglect this coupling. So in classical systems, this is an issue, and if you go to quantum mechanics, it gets even worse. And there is a vast literature on that, but I just separated one representative work by Peter Henge, where he would just study, and that's kind of cute. He would just study a single particle here coupled to a reservoir, to a bath, and Langevin equation, that's not really important. And then he will compute the energy just by taking one of the recipes I discussed before, like you have the Hamiltonian of your system, you take the trace over the whole system, and here you divide by the trace of the whole system, and in this way you derive a specific heat. Or another recipe, like you write down the partition function, and you derive the partition function, and then this is another way to get the specific heat. In case where the usual thermodynamic properties are fulfilled, the two ways of computing give the same result. But here they give entirely different ones, because the coupling is by no means negligible. So you have to think about a way of dealing with this partition, and how would you treat it. And this is, again, an ongoing, let's say, discussion in this particular field, how you deal with the strong, and there are different ways where people are at least settling this issue. We're interested in transport. So back in track, what about non-equilibrium processes? And we're interested in entropy production and other thermodynamical properties. So then going back to classical, in classical systems, it has been solved many, many years ago. Actually, this is probably the first thing that has been solved. And Boltzmann already thought about this. And in his famous H-theorem, he described the evolution of a non-equilibrium kind of distribution to equilibrium, and actually proposed this function here that in modern days you can associate with entropy. And when you are out of equilibrium, this entropy as a function of time, it always grows. And this H function is only, it stays as a constant only when you reach equilibrium. So for bulk systems, based on these seminal ideas of Boltzmann, if you wish, you can also write quantum kinetic equations. And this is a subject which was very well explored in the 70s and the 80s. And now we actually know how you would express the entropy production in transport, in bulk transport, in quasi-statical, close to equilibrium, in terms of Wigner transformation. You write non-equilibrium Green's functions, if you wish, and then there is a way to write them in terms of the spectral function and something else. And that something else has to do with the local distribution, local density of particles. And so you can define a local entropy density, and people have explored this idea to write even a continuity equation for the entropy and entropy production. Basically, not as a big surprise, whenever you have lots of collisions, this quantity is not conserved, and there is entropy production. So now, what happens if you extend these ideas to mesoscopic transport, real small systems? And this is the issue we are going to discuss here today. And so for all purposes, I'll be talking about the mesoscopic electronic system, like 2D system, a zero-dimensional quantum dot, if you wish. And this is a kind of a billiard-like idealization. So you have an island of electrons. They are coupled to reservoirs by this two quantum point contacts. And for all the things I'll discuss today, the phase coherence length of my electrons in this device is much, much larger than the typical size of the device. So I don't have to worry about, let's say, inelastic processes and so. So all sort of inelastic process will occur in the reservoirs or in the leads. So here it's perfectly quantum coherence. This is a system that has been studied in reality. So you have lots of systems that fulfill this condition, and this is what we are going to explore. So there is some little connection with what Luis explained to us today. So I'll divide roughly my quantum dot systems in 3 different limiting cases. One, when the system is really wide open, so 2 QPCs which are wide open. So electrons that want to enter the system, they will just push this fluid, and I mean, it's like, you know, like you don't have to pay any price. You keep pushing the other electrons, and the transit is free. And typically, if you measure the conductance in terms of, let's say, chemical potential or a gate voltage that you control, you see for systems which are typically 1 micron size, you see a curve like that with apparently random fluctuations that people understand sometimes as universal conductance fluctuations. And these guys, they depend on the quantum interference of particles shot here in this billiard, quantum particles shot in this billiard. And this has been studied typically in the 90s, early 2000s, in semiconductor and quantum dots and in a variety of systems later on. If I have the opposite limit of weak coupling, then the situation is quite different. Because if I consider a situation where things are almost pinched off, then this is a Coulomb island. And once an electron wants to come in, it will stay there for a long time, and it has to pay a price, a charging price. It will charge the island, so this has to be compensated by a back gate or the chemical potential, or whatever you want. And typically, what you observe are conductance peaks which are almost equally spaced, and this corresponds to the price you pay to enter this island. And they are very sharp, and what I didn't put here is that their height also fluctuates, but doesn't matter for our purpose. So this is the strong coupling, and this is the weak coupling. And the intermediate regime is actually where the electronic part is more interesting, and it has these funny shapes here. And this is actually the physics that Luis explained to us in the morning, and corresponds to this Kondo regime. So actually, this weak coupling regime, where interactions are important, it's from the thermodynamics or quantum thermodynamics trivial, because it's weak coupling. So when I do the partition of my system into a system and leads and reservoir, the coupling itself contributes with little energy. And so most of the problems I was discussing before, they don't appear. So the problems I discussed before, they are particularly acute here. And this is the subject of this paper I'm discussing today. And what I planned and failed miserably is that we are starting to address this regime, but I don't have anything smart to say so far. So here, the coupling is by no means negligible, and the electronic part is non-trivial. This is nice. So it will take another time, few months to explain. So again, so enough for apologies. Now let's discuss the actual problem that I want to address. So I'll stick to a minimal complexity. So this is my quantum dot, and I'll just do a single resonance, if you will, just for clarity. It can be extended to multi-resonance. This is not a big deal. And I have, the system is out of equilibrium, so it has 2 leads here. And actually, there is a drive which affects the position of this level, energy position of this level with respect to the chemical potentials. And this drive can be periodic or not. So, and this is the most general Hamiltonian I can write for this system. And as anticipated, today, no interactions. So there is a paper that has lots of recognition that tackled the problem using non-equilibrium Green's functions. And basically, they bypass this partition function by actually doing some number of approximations that are not easy to understand, or at least I don't understand quite. So the spectral function is renormalized to a different spectral function. And the non-equilibrium Green's function is written in this, I mean, this is a standard thing. So this is the density, entropy density in equilibrium. And this is their ansatz, which is inspired in quantum kinetic approach. This very same equation appeared for the bulk, so this seems to be a genuine ansatz, except for the fact that the spectral function has been adapted. By doing so, you can write, let's say, energy, entropy, and number of particles, and actually write currents. And by the end of the day, the paper obtained relations which satisfy the laws of thermodynamics, describe the irreversible driving, but fails to give what I would call the limit of very slow driving, the quasi-static limit. And this is what we believe has to do with this funny partition or funny ad hoc assumptions. So to fix that, I'll be quoting this work here. If you have just a single terminal, let's say this guy here, which is no good for transport, it's a minimal model, but you can basically understand how energy or particles move from here to here, but you don't have a real current to the leads. This minimal model you can solve, actually, analytically, and you can actually write the zero order. I mean, if you write everything in terms of powers of the driving, this is the driving, you can, zero order, it's equilibrium, so you copy from any book you like, the grand canonical potential, and then energy is defined, and then you recover easy. You can show easily that you have equilibrium quantities. These are average things, right? So the fun begins when you write the first correction, the first order quasi-statical, and it's reversible, because if you reverse the velocity, I mean, if you undo all your things, you go back, right? And then you have relations for the energy production, the energy flow, and the heat flow. And in second order, then things are interesting because now it's reversible. If you just undo your things, this is gone. So it's quadratic in the velocity. And so you can measure, I mean, here you can obtain what is the work that has been dissipated and what is the heat that flows into your reservoir, if you wish. And so by doing this example, the nice thing is that you have a reference of what happens if you have a single contact, and you don't have to worry about too much about this partition. Now, if you have two contacts, sorry, that's a technical point. So this construction has the following issue. Yeah, so you know how to obtain this quasi-static reversible heat just by deriving or taking the derivative of the static things. And so from the thermodynamic relations, you get this thing here. Now, this is actually not so good if you want to compute a more complicated system. You need a microscopic model. And so what these guys realize, and this is the beautiful part of this paper, is that if you start from the microscopic model and write let's say, the energy average over the bath, and half of the energy average contained in the coupling, you obtain the very same relation. So basically they say, or they show, that in this particular case, the partition that you have to use is to cut it very democratically in half, the coupling, give half of the coupling to the energy contained in the system and half of the coupling contained in the bath. This is what is a result of a calculation. Now, this has several problems, because if you have a multiple contacts, then you have to postulate that all this democracy is valid for all contacts. And more severely, what is bad is that all this theory also predicts things for the first moments, but also predicts what are the fluctuations. Once you fix that, you have no leverage, or you arbitrarily choose one of several ways of getting fluctuations. And people have shown that this is not, let's say, consistent with Jarzynski equality, which is really bad. So it works for the average, but it's an approach which is very arbitrary, and it doesn't work for fluctuations. So in electronic transport, one never really worries about that, because you measure currents, and electrons don't stay at the coupling, they just flow. And so you have no problems with that. But in thermal transport, the symmetric splitting, which was proposed several years ago, many people advocated for it, but the fluctuations turn out to be wrong. So you need a way to avoid the strong coupling problem. And this is what we came up with. So we actually approached this problem by using the Landauer formula. And we basically use this idea that conductance is just transmission. And so we consider a piece of the device as being all the region where you have a coherent phase propagation. And we built up current formulas for electrons that transverse here, and assume that all relaxation processes occur outside this coherent phase propagation. So where actually the measurement is made. So once you made the measurement far away, then sure, the electrons have relaxed, and so into these asymptotic states. So in this way, all these issues about the partition are not there. So we only consider asymptotics. And actually this is good, because within this phase coherent propagation region, we are considering only very low temperature regimes. Basically, the propagation of the electrons is unitary, and we, well, by a couple of lines, you show that the entropy is a constant of motion. So this is a problem and a solution, because we actually postulate the entropy production or the processes of relaxation occur far away. So in thermoelectrics, if you use these ideas, then you basically take this relation, and you can actually relate the entropy production to the current, the heat current, and to the particle current. And well, this is known for a long time, so our theory has to reproduce that. Simple result. Oops. And more generally, in linear response, you have to take all this Onsager tensor, if you wish. And again, you have to reproduce this with your theory. So our theory is, well, it's the scattering approach, based on the scattering approach. So you have a S matrix. And the idea is that if you have a fixed scatterer, then whatever comes in with a given energy, it can be, the energy can be changed by as the electrons traverse this region, they can gain or lose energy, and smoothly go to the scattering states. So basically, one assumes that whatever is injected is in equilibrium, and whatever is, this is injected is in equilibrium, and whatever comes out should be a result of a big scattering process. So another way to look at this problem is to consider this mapping, where you have injection of electrons at both sides and outgoing electrons at both sides. You can actually map this into electrons coming in an equilibrium distribution, coming out in a different distribution due to the scattering. And if you write the entropy production for this, consider the entropy that is injected and the entropy that comes out, then by just writing a number of lines, you get this kind of interesting formula that basically tells you that this is the entropy density that appeared before. And basically, if whatever is injected comes exactly the same out, then the entropy production is zero. So if the scatterer doesn't mess up with your states, then this part is zero, and this relative entropy is also zero. But if within this scattering part you get entanglement, or you get a rearrangement of channels, then you have a simple expression of your entropy production. So this idea has been also explored before by people really thinking about interacting systems. The big thing is, how would you compute the S matrix in these interacting systems? Now, we do a more general approach where we don't write explicitly the S matrix. It could be many levels or anything, but non-interacting. So our let's say approach, basically you write this, whatever comes out, this is the definition, and then you do a Wigner transport of that, and then you do a gradient expansion at the end. But based on that, you can write the formula for the particle current, energy current, heat current, and then eventually also the entropy current. So you have all these things together, and now we want to understand if you have a process where you flash electrons into your system, if you produce entropy, like you would expect by Clausius, and how to quantify it. And an application is, for instance, quantum pumps that people have been discussing since a long time. So that basically you have an external drive that causes some flow, and this is a classical one. And people are still in activity of writing this, of studying these quantum pumps, where you have a back gate where you change, and can have even a quantum point contact where you control or count how many electrons pass through the system. And one of the issues in this quantum pumps is that if you have zero bias, people have been postulating that such systems are systems where you can generate current with the minimum entropy production. And this is one thing that we want to settle. So back to the minimal problem. This is our system. Oops, running out of battery here. And this is the level, and we parameterize like that. So this is the velocity, if you wish. The x dot is the external drive velocity. And basically we consider zero bias. Both sides are the same chemical potential. Can we generate current? And how is it related, the related entropy? And so now it's a little bit technical, so the main ideas are already presented. So you can expand like before in powers of the drive. Here you play the same game, so it's implicitly powers of the drive. And here's the part which is a little bit messy on the algebra, and you can find all this in this paper. But collecting everything, you can write the entropy production as a function of entropy current, sorry, as a function of the heat current, and in terms of some irreversible power that is pumped into the drive, pumped by the drive into the system. So this is a complicated formula which is basically expressed in terms of the S matrix. So the idea is that there is this external drive that will do work, and there is some friction actually in order to cause this current to flow. And once you press or you drive the system, all the work that is necessary to drive it is dissipated in this way. So the idea is that basically within the region where you have phase coherence, there is no entropy production, but we think about inside-outside duality. So the entropy stored in the system, which is expressed by that, is related to this entropy current, which is measured outside. And in this way, you can understand what is the entropy production in the whole system, and not in a subpart. So if you average over one cycle here, for instance, then you get interesting results, like, for instance, that the entropy goes back to the same. And so the energy pumped by the drive is released in form of heat. So the idea now is to extend this to interacting systems. And, sorry, what I didn't mention is that if we apply this to this very simple model of a single level coupled to a single reservoir, we are able to reproduce exactly the same results, right, without being arbitrary about partition. And the advantage here is that this, in principle, the S matrix is a general object, so you can have any number of contacts you wish, and any, I mean, it's not restricted to a single level, right? Okay, so let me come back to an end. So the Landauer-Büttiker approach is nice because it has a big history in mesoscopic systems, and in this particular, and has been shown that actually for charge currents, Landauer-Büttiker and non-equilibrium Green's functions deliver the same results. Now here, it's interesting that Landauer-Büttiker gives a consistent theory, while non-equilibrium Green's function still has a way to go, and people have to understand how you treat partition. So in this sense, we bypass a problem, and we actually know the answer. And this inside-outside duality is the thing that we use to recover the standard thermoelectrics, so first moments, no fluctuation so far, first moments. And so this is what I had to say. Thank you very much.
Questions?